One final thing dealing with bond energies, I just want to review real quickly that as the distance between the atoms grows, for example, the bond in FF versus the bond in II, that the bond energy here is much, much greater. That's a much stronger bond than here. And part of that reason is because in I2, iodine atoms are so much bigger than fluorine atoms that there's that big, big separation between the atoms, the actual nuclei of those atoms. Whereas with fluorine, because they're smaller atoms, the distance between the two nuclei is smaller. That makes the bond stronger, which means that this one has a greater bond energy than I2 does. Okay, well, what about, again, we've talked about this a little bit, but what about when you have two atoms that are the same atom, but they have a different number of bonds? For example, if you have a bond that exists between the same two atoms, if you go from a single bond to a double bond, that changes the bond strength. Okay, and that makes sense because double bonds are stronger than single bonds. But if we look at C2H6, that molecule looks like this. The two carbons go in the middle, okay, and then the three hydrogens go on each of the carbons. And notice that is a single bond. Okay, in C2H2, though, it's a triple bond. And again, because that is a triple bond, whereas here it is a single bond, the bond energy here would be much, much greater bond energy in that one than in that one, simply because it is a triple bond. Okay, so here's a question from a real test. It says a student proposes that the energy of the Xe to O bond in the structure in diagram E, so we're talking about this point right here, is greater than that of the Xe to O bond in the structure in diagram D. Either this one or this one or this, it doesn't matter. All three of them are single bonds. So let's just leave the one on the left there. So do you agree or disagree with the student's claim? So they're saying that in diagram E, this one, the bond energy is greater than that in D. So do you agree with that statement? Absolutely yes. We're going to agree with that statement, and all you would have to say is that the XeO double bond has a greater bond energy than the single bond XeO in diagram D. Okay, and even if you think of like a molecule like this, like CH3, C double bond to the O, single bond to the O, and then an H. Okay, that's actually the Lewis electron dot diagram for acetic acid, HC2H3O2. Okay, but notice here we have a carbon-oxygen single bond. Here we have a carbon-oxygen double bond. So again, which of those two bonds would you expect to have a greater bond energy? Absolutely this one, okay? This top one here, greater bond energy than this one, because again, the double bond it takes more energy to break that bond. And again, that's what makes that bond stronger. Coming back up here to this table, remember these bond energies, when you talk about these bond energies, that's how much energy it would take to break that bond. It's also the amount of energy it takes when that bond is formed, which is why when these examples here, that's why these examples work, because it goes both ways, in that it's how much energy it takes to break the bond. It takes 154 kilojoules per mole to break that fluorine-fluorine bond. It also means that when two fluorine atoms come together and create a bond, it releases 154 kilojoules of energy. So here's that video that I was talking about the other day. So this is the young lady that was the candidate for Miss America, and she actually did end up winning. Okay, but just listen to what she says as the reaction is going, and I'll pause it right after she says it. It's kind of a cool demonstration, but at the same time, listen to what she says about it.
But be careful, don't try this one at home. Now, in my flasks are concentrated hydrogen peroxide Heat is formed from the breaking of the bonds within the hydrogen peroxide molecule.
Right there. See how it says the heat is formed from the breaking of the bonds in the molecules. Okay, that's the part that, again, a lot of people think that, oh, you're breaking the bonds, that's releasing lots of heat. No. Anytime you break a bond, it's always, always, always going to require energy to do that. So no, in that instance, it's not giving off heat when those bonds are broken. It's giving off heat when that hydrogen peroxide, H2O2, so those bonds have to be broken to form H2O and O2. And let's see, I don't know if it's in this chart. I think it is. I'm looking for the HO bond energy, and I don't see. Oh yeah, there it is. So if we were to look at this, let's look at when that energy is released. So we have HOOH making, and we need to balance it. Sorry, I didn't balance it. Let's see, we've got 3, so we need 2 here, and this will actually be a good example, and then we need a 2 here. So there's 2 H2O2. So when there's more than one of them, like in this example we did the other day, or you were supposed to do the other day, if there's 2 of them, make sure you draw both of them so you can see all of the bonds that are being broken. That's a big, big help right there. Don't try to do this without drawing the Lewis electron dot diagrams and showing all of the bonds. Okay? So this is what we have here for this one. So in that example, and again, I'm going to do this the quick way. So I'm looking to see what things are the same. So 1, 2, 3, 4. There's 4 HO bonds, 1, 2, 3, 4 on both sides, so they cancel out. So we're breaking 2 oxygen single bonds. Oh, and that's the one I don't see anywhere. I don't see the oxygen. I see carbon and oxygen, but I don't see oxygen. All right, so I just looked it up real quick. The oxygen single bond, which again, that's what we have right here. We have 2 of those. So we've got 2, and that value, I just looked it up online, is 146 kilojoules per mole. So that's our positive part. And then our negative part is, again, all of these bonds cancel. So we just have that oxygen double bond, which again, in O2 is 498. So 498. So that is our negative side. That's our energy releasing part. So make sure you subtract those 2. So 292, which is 146 times 2, minus 498. That reaction is absolutely, and you saw it in the video, you saw that steam coming up from it. That releases 206 kilojoules per mole of energy. And remember that it's not when the bonds are breaking. It's not when the bonds are breaking. That's the part that requires energy. It's when that oxygen molecule is formed. When that O2 molecule is formed, that's when all that energy gets released per mole of oxygen that is produced.